Welcome to Shanti-Peace for Mathematics. In this video, we'll talking about the compatible system of first order partial differential equation. So first of all, let us see what is the definition of compatible system of equations. So the equation that is f of x, y, z, pq. So that is the first order partial differential equation is there equal to 0, where p is del z by del x and q is del z by del y. So they are the partial derivative of z with respect to x and y. And there is another partial differential equation of the first order is given, that is g of xyz q equal to 0. If you want to say they are compatible equation on a domain D, if the first one, a j, that is a Jacobian of del fg upon del pq, should be non-zero on whatever the domain D. Domain is the open connected set, so it is a subset of R square. So this Jacobian is non-zero on that domain, and the second condition is required is the p equal to phi of xyz and q equal to some function of xi of xyz are obtained by solving. If I can solve, this is the first equation and this will be the second equation. So it's obtained by solving the first and second equation, by solving first and second redundant, that is dz is equal to phi of xyz dx plus xi of xyz dy is integrable. Integrable means it is a solvable. So it is a Pfaffian equation kind of thing. So if this Pfaffian equation is solvable, and when we can, and this Jacobian is non-zero, then we can say that this two function f and g, both of them are compatible. That means they can able to have one common solution between them. Now there is one important result due to this compatible differential equation is there. That result is this: a necessary and sufficient condition for the integrability of this equation, that is dz is equal to phi of xyz dx plus xi of xyz dy, is box fg. This box is 0. Now what is this box? It's defined as del f upon del fg upon del xp, that is a Jacobian of fg with respect to xp, into p into del fg upon del zp plus del fg upon del yq plus q into del fg upon del zq equal to 0. If this is equal to 0, then this is the necessary and sufficient condition for this equation is integrable. So ultimately the necessary and sufficient condition for the two equations, that is f and g, as we have defined in my previous slide, that is these two equations are compatible, is this, that is box of fg is 0. Now this is a Pfaffian differential equation that we have here, and we know that a necessary condition for Pfaffian differential equation is integrable is x bar dot curl of x bar is equal to 0. So we'll start with this concept and we'll go further with that. So let us try to prove this statement. Here we have this equation is dz is equal to phi of xyz dx plus xi of xyz dy. Therefore, this equation can be written as phi of xyz dx plus xi of xyz dy minus dz is equal to 0. So we note that here what is your x bar here, that is if you have equation p dx plus q dy plus q r dz equal to 0, then your x bar is pqr. So here x bar is, I am just writing phi xi and minus 1. So we will calculate what is the curl of x bar here. So curl of x bar as per the formula of the curl will have del by del x, del by del y, del by del z, phi, xi and minus 1. And we know that this phi and xi are the functions of x, y, z. So we will expand this determinant here. First we have del by del y with respect to minus 1 will gives me 0. So this will gives me minus z, xi z. Then the second one, it is already a minus sign is there. And the derivative of minus 1 with respect to x will gives me 0. A derivative of phi with respect to z will gives me minus, so that will be plus phi z, and then you will have it is xi x minus phi y. Now we need to calculate what is curl of x bar into x bar, and that has to be 0 because this is given this, let's say this is the equation number 1. So if equation 1 is integrable, if and only if we know that x bar dot curl of x bar is 0. So therefore this will gives me if and only if what is x bar is phi xi minus 1, and curl of x bar we have calculated is minus xi z, phi z and xi x minus phi y. The dot product in between this is equal to 0. So therefore this will gives me phi into xi z minus plus xi into phi z minus xi x plus phi y equal to 0. And if I can consider this, or I can rewrite this one as xi of x plus phi into xi z equal to phi y plus xi into phi z. Now on substituting phi and xi for the p and q into the differential equation f of xyz and differentiating with respect to xyz, will get, that means what I'm talking, we have this f of xyz pq equal to 0. And if I substitute this value of p and q here, that is the value of p, we know it is p equal to phi and q equal to xi of xyz. If I differentiate this with respect to x and z, so differentiating with respect to x and z, we get, now what is the situation? F is a function of x, y, z, p and q, but this pq is a function of phi, but this pq are a function of x, y, z. So this is the situation we have, and this p is actually phi function and q is actually xi function. So when you are differentiating this with respect to x, there will be 3x is here. So you have to go by 3 paths. The first one is fx, that is this part. The second one is del f by del p. So I'll just write plus fp into del p by del x. So I'll say that is 5. So it is 5x plus fq, that is del f by del q, and then del q by del x, but q is xi, so that is xi x equal to 0. Similarly, if you differentiate this with respect to z, that will give you fz plus fp phi z plus fq xi z equal to 0. Now I'll multiply the second equation of this one. So if I can say this is a star and this will be the double star. If I multiply the double star equation by 5, so I'm multiplying, so I'm doing this operation, multiplying this double star to 5 and then adding into the first one. If I do this one, we get, you just see that if I multiply this equation by 5, then every quantity is multiplied by 5 here, and we have to add this. So it is fx plus phi fz. So we'll have fx plus phi fz plus we'll have fp is common out from that, both of them, that is phi x plus phi z. So fp is common, we'll have phi x plus phi z plus in the next term you will have fq is common out and you will have xi x plus phi xi z. So we will have fq plus xi x plus phi xi z equal to 0. And what we have did is for f, we have started with, you just see that we have started with the function f and we have obtained all the things which we have got here. Now similarly, we may deduct from the equation g of xyz pq equal to 0, that instead of f, if I start with g, we'll have similar kind of result. That means gx plus phi plus gp phi x plus phi into phi z plus gq xi x plus phi xi z equal to 0. Now solving these two equations. So to solve this two equation means, if I can say this is the equation number 3 and this is equation number 4, I will solve this for xi x plus phi xi z. So for that, so to solve this equation number 3 and 4, we multiply the equation 3 by gp and equation 4 by fp. So this term will be eliminated and we have this term. So what I will do is, the equation 3 is multiplied with gp and subtracted from the equation 4, and that is multiplied with fp. What we will get? You just see that if I multiply this is by gp, then we'll have it is gp into fx plus phi fz minus, here you will have this, so this will be multiplied with fp, so you will have fp into gx plus phi gz. This middle term will get cancelled out because it has the same quantity, because this is multiplied by gp and this will multiply by fp, so that will cancel. Here you will have gp into fq, so plus gp into fq, in bracket it is xi of x plus phi of xi z minus, here when you multiply this is by fp, so this is fp into gq it is Fp into Gq phi x plus phi xi z equal to 0. And if you simplify this one, you will have phi x plus, sorry, xi x plus phi xi z equal to, you will have in the numerator, you just observe, you will have this, that is Gp fx plus phi Gp fz minus Fp gx minus phi Fp gz. In the denominator you will have Gp fq minus Fp gq. This is Gp. Now what is numerator? You just observe this two terms and this two term. The first term and this term. So what we have, therefore, xi x plus phi xi z equal to. You first note that what is the function or what will be the Jacobian. Jacobian of fg upon fxt will be fx fp gx gp. So if you expand this one, this is fx gp minus gx fp. So you just observe that is exactly the same thing we have. That is fx gp minus fp gx. Fx gp minus fp gx. So that is del f del g upon xp plus this phi is common out from this two. So plus phi into, in the similar manner, we'll have here it is del fg upon del zp, which you can say that it is fz fp gz gp. If you expand this one, it is fz gp minus fp gz. And you just observe that as per this one, it is Gp Fz is there. So it is Gp Fz. So that is del F G upon del Zp. And the denominator you just observe, the denominator, it is actually del F G upon del Pq. That is the Jacobian that we have denoted as J. So it is 1 upon J is there. And now I don't want required this whole terms here. So I just cancelling out from here. Because I want to do some further calculation here. To be continued with this. Now, what we have did this one, we have did by starting a differentiating this equation with respect to x and z. We obtain this equation and then we'll do this. We have this equation and the same procedure we did for g, we have this, and by solving this two, we got this expression. Similarly, if you differentiate the given pair of equation, that is f of xyz pq equal to 0 and g of xyz pq equal to 0 with respect to y and z, we obtain. So instead of doing this everything we have did for x and z, now we will do the y with respect to y and z. We get similar kind of result and we do some analysis and we obtain that equation is in this form, that is phi y plus xi phi z equal to 1 upon Jacobian, which is of minus sign, del f g upon del y q plus del f g xi into del z q. And if I call this previous equation, that is this equation, as the equation number 6, and this is as equation number 7, whatever the equation number is there, I think so it is 4, 5, 4, 5th, 5th and 6th. So if I can say this is the 5th equation and this one is the 6th equation, and if you substitute this value of, see, you can have this equation now. Here we have this equation. This is the main equation. I can say this is the main equation because from this we have obtained all the things. Due to this we have done everything. So we have considered this side, we obtained this side, and we obtained this side. So this value of this equation number 5 and 6, on substituting from 5 and 6 into the equation number 7, so whatever the main equation is there, and replacing phi and xi by pq, p and q respectively, what we will see? We see that, so what we got on one side, it is 1 upon j del f del q upon del xp plus phi into del f del g upon del zp is equal to, on the other side it is minus 1 upon j del f del g upon del yq plus del f del g upon del zq is there. I have to take everything on the other side, and this 1 upon j will get cancelled because as per our hypothesis it is compatible, so this j has to be non-zero. And if you can take this one on, this is xi, here xi is missing, and if you replace this xi as p value and this phi as p value and xi as q value, what you will get, it is box of fg is equal to 0. So, and that completes the proof of this necessary and sufficient condition for the two equations are compatible equations. We'll write one note here which tells you that a solution of this dz equal to phi of xyz dx plus xi of xyz dy is of the form capital F of xyz c equal to 0, where c is arbitrary constant, or I can say arbitrary parameter, and hence we assess that from this, if the equation, that is small fyz pq equal to 0 and g of xyz pq equal to 0, is these two solutions or these two are compatible, then they are one parameter family of common solution. That is a one parameter family of the common solution is there. So what is the note? The main things which we can mention here is the equations, that is f of xyz pq equal to 0 and g of xyz pq is equal to 0 are compatible, then they have one parameter family of common solution. Let us do one example of compatible differential equation and we'll finish this video with that. So let us have this example, so that the equation, that is f is equal to xp minus yq minus x is equal to 0, and the another equation g, that let's consider it is x square p plus q minus xz is equal to 0, are compatible, and find a one parameter family of common solution. So the compatible means there is a common solution is possible and it is one parameter family of the solution is there, that we need to obtain for this example. So first of all we need to observe that this system is compatible. For that you have to consider, you just recall what is the definition of the compatible equation. The first one is the j that we have, it is del f by del fg upon del pq should be non-zero. That we need to check. So here the function f is this, so we have fp. Here we have fp is x, fq is minus y, gp is x square, and gq is 1. So if I can calculate this Jacobian, j is equal to, that is fp, fq, gp, gq. We have obtained it. fp is x, fq is minus y, so it is x minus y. gp is x square 1, so it is x square 1. So if you expand this one, you will have x plus x square y, and this x is common out, so you will have x into y, and this is non-zero. Then and only then the solution is possible. So on this domain, so what is my D? It is a set of all points x, y such that x is not equal to 0 and x plus x into y is not equal to minus 1. So my domain D is this set of all points in R2 which satisfy this. That is my domain D. On this domain, and now we need to obtain the solution for the compatibility. So for that I need to have the value of P in terms of xyz and Q in terms of xy. So we have the two equation is given to us, that is xp minus yq minus x is equal to 0. The other equation is x square p plus q minus xz is equal to 0. These are the two given equations. We need to obtain the value of p in terms of xyz and q in terms of xy. So what I'll do is I just multiply this equation by y. So multiplying this by y, we'll have x square py plus qy minus xyz equal to 0. And if I add this to equation, that is xp here minus yq minus x is equal to 0. If I add them, this will get cancelled out. So we'll have p into x plus x square y. If I take this two quantity which are in minus sign, which I am taking on other side, and if x is common out from both of them, so it is x into 1 plus yz. So the value of p you will have, it is x into 1 plus yz upon x into 1 plus xy. See, this denominator's quantity is not in our domain, so that's why the value of p is this. And similarly, if you want to calculate the value of q, then what you have to do is you have to multiply this equation by x. So if you multiply this equation by x, this is x square p minus xyq minus x square equal to 0. And if I add this two, then it will have x square p plus q minus xz is equal to 0. So if I add them, well, this is cancel out. If I take minus sign here and minus here, and this become minus minus plus. So this will gives me q into 1 plus xy, if I take minus out, is equal to, here it is xz minus x square. So the q value of q is x is common out, you will have z minus x upon 1 plus xy. So we'll have the value of p and q in terms of x and y. So now we'll start with this equation, that is dz is equal to phi of xyz dx plus xi of xyz dy, where phi is the value of p and xi is the value of q. So the value of phi, we can substitute 1 plus yz upon 1 plus xy dx from this x is cancelled out, we will have this value, and plus the value of xi is x into z minus x upon 1 plus xy into dy. This is a Pfaffen equation, and the question is to obtain the solution of this Pfaffen equation. And it is up to you that you can deal with the Pfaffen equation as per my previous video. You can see the link in the description here in the I button. If you have not gone through that video, please go through it and how to solve this type of Pfaffen equation. Now we'll subtract dx from the both sides. So that will gives me dz minus dx is equal to 1 plus yz upon 1 plus xy dx minus dx, so I will just subtract minus 1 from here, dx plus x into x into z minus x upon 1 plus xy dy. And if you simplify this one, this will give me 1 plus yz minus 1 minus xy upon 1 plus xy dx plus x into z minus x 1 plus xy dy. So observe that this 1 is cancelled out, and from this y is common out, and a left quantity is y into z minus x. So you will have dz minus x on this side, it is equal to y z minus x upon 1 plus xy dx plus x into z minus x upon 1 plus xy into dy. Now just z minus x is common out, so we'll take onto the other side, that is z minus x, and this will be gives you y dx plus x dy upon 1 plus xy. The numerator you just write down as dxy because the derivative y as it is derivative of x, x as it is derivative of y, the way it will be written as d of xy plus xy, d 1 plus xy. Now if I take the integration both sides, integrating, we get this is ln of z minus x because it is d of z minus x upon z minus x is there. Here it is a derivative of this one is numerator, so that is ln of 1 plus xy plus ln of some constant c is there, and this will be written as z minus x is equal to c into 1 plus xy. So finally you will have the solution is z is equal to x plus c into 1 plus xy. So hence we can say that the given two equations, differential equations, are compatible on D. A D is a set of all values where x is not equal to 0 and 1 plus xy is not equal to 0. Because this z phi dx plus xi dy is integrable, and the solution we got it is x plus c into 1 plus xy is one of the parameter family of the common solution. One should note here that if you want to check that it is whether these two equations, the given equations, are compatible, then you can also check that this box Fg is 0. What is the definition of box Fg? Is del Fg upon del xp plus p into del Fg upon del zp plus del Fg upon del yq plus q into del Fg upon del zq. If this quantity is 0, then also we can say that the given two equations are compatible. And with this note, I can also tell you that if you have a compatible two differential equation, that is f of x, y, z, pq equal to 0, and g of x, y, z, pq equal to 0. These are the two differential equation is there. It is not necessary that every solution of first equation that is equal to 0 be a solution of the second equation, or vice versa. That means any equation, any solution of this one will not be a solution of this one. It may happen that both of them have a different solution. But the compatible means that both equations should satisfy. For example, in this example, we have considered our equations as xp minus yq minus x is equal to 0. That is my f function. And the g function that we have considered x square p plus q minus xz is equal to 0. Now the solution of the first function f, it also have z is equal to x into y plus 1 is there. But this is not a solution for the function g. And similarly, there is a solution of this function g is z is equal to x plus y upon square root of 4. But this solution is not a solution for the function f. So in that manner, one of them may be a solution, but the solution will not be for both the equation. So compatible means this. In this previously what we have discussed, this is the solution which satisfies the both the equation. With this note, I'll give you one exercise to solve by yourself. That is, if you have a function f is equal to p square plus q square minus 1 equal to 0, and g is p square plus q square x minus px into z equal to 0. Check whether these two differential equations are compatible. If so, find the one parameter common family of the solution. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.